Okay, I will begin because in any case, we begin with a sort of review of what we're going to do in this lecture. So welcome everybody to the third lecture of QIT Advanced Topics. In today's lecture, we are going to really talk about mainly the notion of passivity, which is a very important notion in quantum thermodynamics that is essentially based on the concept of how much, or the quantity of how much work you can extract from a quantum system by doing a unitary operation on it. And we're going to start with passivity, which talks about doing a unitary on a single system. And eventually we're going to get to complete passivity, which talks about doing unitaries on many copies of the system. But in between, we are going to talk about majorization, which is an extremely useful mathematical tool for thermodynamics, or well, actually for many things in physics. Those of you who will do entanglement and non-locality will find it useful in there as well. But specifically for finite dimensional quantum thermodynamics, majorization is a very important tool. So these are sort of the topics that we will go through today. And the goal is to end with the proof that the only states that are completely passive, that is the only states that you cannot extract any work from, even if you have many copies of the state, are the Gibbs states, which is essentially puts the thermal state on a very special footing compared to the rest. And this will also be the first example for us of what we call a resource theory in thermodynamics. That is a theory that in which we are given a set of allowed operations and we are asked to find out what are the constraints on what we can do in the theory and what are the free states of this theory. And all of these concepts will become clearer as the lecture progresses. I don't know whether we will have time after that, but if we do have time, we will discuss briefly Jaynes' principle, which is an information-theoretic manner at arriving at thermal states, as opposed to the work extraction manner in which we will arrive at it in this lecture. Okay, so to begin, let's talk about the concept of passivity, which starts with the concept of ergotropy. So the ergotropy is very simply defined as the work that you can extract from a quantum state under a single unitary operation. So we know that if you have a density matrix rho and we do a unitary on it, you go to rho u dagger, and that gives you a change in energy, delta E, of trace of h u rho u dagger, which is the final energy, minus trace of h rho. And what we will look at is minus of delta E, which is the work extracted. Essentially, what we say is we don't really look into the details of how this unitary is performed. But given that the unitary has been performed and given that total energy must be conserved, if the system decreases in energy, so if delta E is negative, the final state has lower energy than the initial state, then we assume that, well, we don't assume, we conclude that difference in energy is reflected as an increase in energy on the battery or whatever machinery performed the unitary operation. And so the ergotropy is defined as the maximum over all of the unitaries of this difference, the negative of delta E. So trace of h rho minus trace of h u rho u dagger. And we call a state passive. So this is given by, I'm going to call it capital epsilon for now. We call a state passive if and only if the ergotropy of its density matrix is equal to 0. Meaning that any unitary you do on it, you will only manage to increase its energy. So you can only provide energy to the state by doing a unitary operation. You can never extract energy from it. Now, given the discussion that we had about virtual qubits and virtual temperatures, one very easy thing to see is that, inversions, and by inversions, I mean a higher energy level has a higher population than a lower energy level, always are the same as this is the same as saying the state is non-passive. And the reason is very simple. If you have some Hamiltonian, let's just take a single qubit. So this is state 0 and 1, and it has a energy gap E. So I'm really labeling it so that the state 1 has a higher energy than the state 0. So 0 is the ground state. And if I have a population in the ground state that is lower than that of the excited state. So imagine that I have a population of 0.4 here and 0.6 here, so that the state is 0.400 plus 0.611. Then it's very clear that if I do the unitary that simply swaps these two states, I will extract energy. So if I do the unitary, which is, well, it's essentially the X ergotropy. This is also the same as saying, using the language of virtual temperatures that we had, that if we have any beta virtual that is less than 0, that's the same as saying that it's a non-passive state. Because remember, if beta virtual is less than 0, then the Gibbs ratio e to the minus beta virtual delta E will be greater than 1, because beta virtual is less than 0 with the minus sign, so you get a positive exponent. And that will mean that the higher energy has more population. So it's very clear that inversions and negative virtual temperatures are intimately related with the notion of passivity. In addition, it is also the case that any state that is non-diagonal in energy, or rather non-block diagonal, meaning that it has a coherence between two different energy levels, is also non-passive. I'm not going to prove this because once we discuss majorization, this will be very clear. But the end result of these two statements is to say that rho is passive if and only if it is diagonal. And the second is ordered in energy, meaning that, or rather so ordered to be decreasing in energy. This means that if I look at the eigenvalues of the density matrix and it's diagonal in energy, so these are just the populations have to be ordered decreasing with respect to increasing energy. So higher energy levels must have lesser population. Okay, so this is a very simple introduction to the notion of passivity. And of course, there are many, many passive states. As you can imagine, any state that is ordered in energy is going to be passive. This includes thermal states, or rather this includes Gibbs states, which are the ones where we write rho is e to the minus beta times h, where beta is greater than 0. So any state with a positive temperature, any Gibbs state with a positive temperature is going to be passive by definition, but passive states are much more general than that. You have many more passive states. Okay, so now we're going to discuss a little bit on the notion of majorization. But before I proceed, are there any questions on just the definition of passivity and what it means? Nope. All right. So let's continue now with, with the notion of majorization. Okay. So the definition of majorization is very simple. It simply is an ordering or a relationship between vectors. So if I have two vectors A and B, whose elements are both real numbers, and it also turns out that the sum of all of the elements, so the sum of the elements of AI is equal to the sum of the elements of BI, then I say that A majorizes B if, now I do two things. First of all, I construct the vectors. So I construct the vectors A decreasing and B decreasing, which are the same as A and B, but I simply order the elements to be in decreasing order. So whatever they are. So for example, if A is 0, 2 over 3, 1 over 3, and let's say B is just a completely mixed vector, then A ordered is going to be 2 over 3, 1 over 3, 0. B ordered is going to be the same as B because all of the elements are equal. So I construct A ordered and B ordered, and then I check that every partial sum, so for any K, the sum of the largest elements, the K largest elements of A is greater or equal, AI, is greater or equal to the sum of the K largest elements of B. And if this is true for all k, I say that A majorizes B. So vector A majorizes B. So example here, we can compare the two vectors A and B that we have here. This is A and this B ordered is the same as B. So B is equal to B ordered, which is that. And I see that A1 is 2 over 3, which is greater than 1 over 3, which is B1 when ordered. And A1 ordered plus A2 ordered is equal to 1, which is greater than 2 over 3, which is the value of B1 ordered plus B2 ordered. And of course, the sum of all three elements is the same, it's equal to 1. So in fact, majorization is defined regardless what the norm of the vector is, the total sum of elements. But we will only apply majorization almost exclusively to normalized positive vectors, meaning that they're essentially property distributions. All of the elements are between 0 and 1, and the sum of the elements it totals to 1. Okay, so this is the basic definition of majorization. Note that it is not, as defined, it's not an order of any sort because it doesn't depend on the ordering between the elements. So if I give you, for example, A and A ordered, by the definition of majorization, they both majorize, sorry, so the symbol for majorization is a bit different. And also A ordered majorizes A because the ordered elements are the same, but they're not exactly the same vector. A is not the same as A ordered. So it doesn't form an order of any sort. However, if it is the case that you have a pre-ordering of elements, so you can either do this by restricting yourself to vectors that are ordered to be in decreasing order, or just define this majorization on equivalence classes rather than on individual vectors, then it does form a partial order, in the sense that if A majorizes B and B majorizes C, then you will have that A will majorize C and so on. But it's not a full order because there are some vectors that cannot be compared. So for example, so it is a partial order. And a very simple example would be these two vectors. So just take 0.5, 0.25, 0.25, and the other vector 0.4, 0.4, 0.2. The largest element of the first is greater than the largest element of the second. But if you take the sum of the first two largest elements, this is 0.75 in this case. And in this case, it's 0.8, which is greater. So it's the opposite way around. So these two vectors have no relationship based on majorization. Neither of them majorizes the other. Okay. From the definition itself, it's kind of clear to see which is the vector that majorizes all others. And that is the pure state. So if I have some zeros, a single one, and then again a lot of zeros, this majorizes every other vector. And here I'm really restricting to the case of vectors that are property distributions so that the sum is always 1 and they're always positive elements. And the reason is quite simple. If I take this vector, the partial sum, the largest element is already 1, and every sum of the largest k elements is just going to be 1, which is the largest sum that you can ever have from taking of a subset of the elements of a property distribution. So this is going to majorize every other vector. And then on the other extreme, if you ask, is there a vector that is majorized by every other vector? Then you get the maximally mixed distribution, where D is the dimension. This is majorized by every other vector. I will not discuss sort of the proof of this because you will in fact do it within the tutorial, but it is a simple question. And for those of you who have done the QIT course, thinking of Fourier transform basis should make this very clear as to why you can do this. Okay, it's not a coincidence that the two vectors that we've picked somehow seem to be the case of the pure and the maximally mixed state. If you think of these as diagonal density matrices, then one of them would be the set of pure states, and the other one would be the set of, well, not the set, but the single maximally mixed state. And the reason is because majorization does correspond in some fashion to mixing. If A majorizes B, we can associate B with being somehow a mixture of elements of A. And the way to understand this is via the following statement.
Sorry, may I
Is
ask?
there a question? Yes. Please
In the
do.
definition of majorization, B seems to be ordered, but A doesn't. Is that a typo or?
No, it's not a typo. So I purposely began with A not ordered, because what majorization does is it first orders the vectors and then it compares the sums. So majorization compares the sum of the largest k largest k elements, basically. So first you take the ordered thing and then you look at it. Okay, so this is why I started with A.
In this expression, both A and B are ordered.
Sorry, which expression are you talking about? The example in which I gave that was not?
No, for all k.
Yes.
Sum of.
Oh, I'm sorry. Yes, sorry. I see what you mean by the typo. Yes, this, you mean that I didn't write A ordered.
Sorry.
Yes, you're right.
Thank you.
Yeah, that is a typo. Thank you. No. Thanks. Okay, right. So to continue now, we look at the following theorem. Who is this by? Oh, I'm not exactly sure who this is by. Probably either Birkhoff, Schur, or Horn. But there is a theorem which is that if, let me not scroll too quickly. Okay. If A majorizes B, then there exists a doubly stochastic transformation D such that B is equal to D times A. And the doubly stochastic transformation is essentially a matrix. So this is the same as saying, if I write this as a vector equation, Bi is the sum over J, Dij times Aj. So this is now a vector is equal to matrix times a vector. And doubly stochastic means that the sum over the rows and the sum over the columns are both equal to 1. And also Dij is greater than 0, greater or equal to 0. So a doubly stochastic transformation is a matrix that transforms a vector where all of its elements are positive and its rows and its columns sum up to 1. Okay. And the fact that the columns sum up to 1 is actually quite simple to see from the conservation of probability, because if the columns don't sum up to 1, you can start with a normalized vector and end up with a non-normalized vector. So that just follows from conservation of probability. But the fact that the rows sum up to 1 is a different is a further constraint that essentially tells us that this transformation cannot concentrate the elements of the vector. It can only mix them. I'm not going to. This is sort of a hand-waving way of saying what is going to come next. But just to go back to our example, where B, I'll write it down again. B was 1 over 3, 1 over 3, 1 over 3, and A was 0, 2 over 3, 1 over 3. We can see that if I write it down as a vector, so 1 over 3, 1 over 3, 1 over 3 is equal to, and now I want a 3 by 3 vector that will affect this transformation. And I can construct one quite simply by saying, well, if we leave the third element unchanged, this is already enough for us. And between the second and the first element of A, all I have to do is to split the second element and put it over the first and the second element. So if I have a half here and a half here, this will already do what I like. And at the moment, I don't have to actually put the first column in at all because A has a 0. So whatever numbers we put there, this equation is already true. But because it's doubly stochastic, I need that everything has to sum up to 1, every row and every column. And as a result, the only way of completing it is in this fashion. So you see now B is given by a doubly stochastic matrix times A. Okay. Right. The reason that doubly stochastic matrices are quite simply understood as mixtures is from the following theorem. And this is now the Birkhoff-von Neumann theorem. And that one says that every doubly stochastic matrix can be understood as a convex combination of permutations. So every D is given by a sum over, let's say, n, qn, pn, where these are permutations. And this is a convex combination, which means that qn is greater than 0, sum over n of qn is equal to 1, which is the same as saying that, 1, not the identity. This is the same as saying that Q itself is a valid property distribution, which is also the same as saying that you can do a doubly stochastic transformation with a particular probability picking out of a set of permutations. Right, so the example that we currently constructed, we can quite simply say that, so the matrix that we had, half, 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 0, 0, 1, we can easily see this as half of the identity matrix plus half of this permutation, which swaps between the first two elements. So, sorry. Or in other words, half times identity plus half times the swap between elements 1 and 2. Okay, so this is rather useful because it means that if you look at the set of all doubly stochastic matrices, this is a convex set. And the extreme points of this convex set are the permutation matrices. So if anybody is used to the language or has been introduced to the language of polytopes, another way of saying this, and this is not important to understand for this course, but it is a useful geometric way to see this. If you write the doubly stochastic matrices in terms of putting every one of their elements as some coordinate on the real line, then you will get a very high dimensional space in which the doubly stochastic matrices will be a set. And this set will be a polytope, which is the higher dimensional version of a polygon, for example, in 2 dimensions, where the vertices of that polytope are effectively essentially the permutation matrices. And every point within that polytope can be written as a mixture of the vertices, just like in the case of polygons. Okay. Now, the reason why it's very nice that the doubly stochastic matrices are a mixture of permutations is because of the following. Imagine that we want to optimize a linear function. And what do I mean by this? So I have a function f of a vector v, which is a convex combination of the elements of v is equal to 1 to d. So sorry, I said convex. I didn't mean to say convex combination. It's a linear combination of them. So for example, fi could all be they're all in R, for example. And so this is a function that takes you from R to D onto the set of real numbers. And I want to find out, given a initial state V, I want to say, well, if I am allowed to do any transformation that I like on this, any doubly stochastic transformation, what is the transformation that will give me the maximum value of this function or the minimal value of this function? So for instance, one function could be the following. I could, and this is, I'm picking this to be sort of similar to a Hamiltonian. So imagine that I have 3 energy levels, which are labeled, which have the energies 0, E, and 3E. Then I know that the average energy would be given by, so the trace of this Hamiltonian times rho, which I know I can write as P0 times 0 plus P1 times E plus P2 times 3E, if I call these states 0, 1, and 2. So I'm going to pick the function now to be like this. It's going to be 0 times V0 plus E times V1 plus 3E times V2. Okay? And I want to optimize this. Now, the nice thing is that if I have a function that's like this, and I have a transformation V that I have a doubly stochastic transformation of V, then I know that Vi prime is equal to the sum over ij of Dij Vj. or rather, sorry, let me put it this way. Yes, Dij. But this in turn is equal to each Dij is a convex combination of permutations. So this is going to be sum over I, j, and n. And this is going to be the sum over n of the permutations Pn, Ij, Vj, which is sum over Ijn of, oh, sorry, I already had n. I'm going to shift the permutation n as a subscript here. Sorry for the abusive notation, Vj. So if I have a linear function, sum over fi vi prime, so this is the function on the final vector. This is the same as the sum over I of fi, and this can be written as sum over n. I in fact don't even need the ij subscripts from the doubly stochastic matrix, Pn times v. But these are both finite sums, linear combinations, so I can easily switch them around, and this will become sum over n. Sorry, there's a qn here, and a qn here, and a qn here. Sum of n qn times sum over I fi times Pn of v. And what I've ended up with now is, since every doubly stochastic matrix is a convex combination of permutations, I find that the final value of the function is going to be a convex combination of what the values of the function are on every permutation of the original vector. And by the fact that a convex combination of numbers is always lies between the range of those numbers. So a convex combination of two numbers is guaranteed to lie in between them. In a similar way, a convex combination of n numbers is going to lie between the minimum and max of these. It follows then that f of vi prime is going to be less than the max of f of Pn times vi. Sorry. And this is going to be greater than the min of f of Pn times v. So I have been slightly sloppy here. This is actually just v, v. There's no need of an I here because these are just the vectors v. All of this is to say that given a doubly stochastic transformation that we're trying to optimize over, or a function that we're trying to optimize over, all we need to do is to check what the values of this function are on permutations of the vector that we have given initially, and the maximum value and the minimum value are going to be obtained on those permutations. So returning back to our example that we had, imagine that I was given that v was a, which was 0, 2 over 3, 1 over 3, then it's very clear that the max of f of v, which I chose, is going to be the function acting on the vector 0, 1 over 3, 2 over 3, because this is the vector that puts the maximum population in the highest energy and the minimum in the lowest. And the minimum of f of v, v prime rather, is going to be when I arrange the populations in the other way. So given any linear function, it's very easy to check what is the vector or the permutation that does the best and the least value. It's simply the one that orders the populations either the same way that the coefficients of the function are ordered, or in the opposite way, depending on whether you want to get a maximum or a minimum value. Okay, are there any questions at this point? Nope. Okay. Right. So I'm going to continue now by returning back to quantum mechanics. What is the relationship between this and the quantum mechanics? This is due to a very nice theorem called the Schur-Horn theorem. And what the Schur-Horn theorem states essentially is that there's the eigenvalues of a matrix and the diagonal values of a density matrix are essentially related to one another by majorization. So one way of stating the Schur-Horn theorem is the following. Imagine that h and lambda are both vectors in Rd. So they're both vectors of real elements, and the sum of them, the sum of the vectors are the same. So they have the same norm. And by norm here, I just mean the sum of the elements, not the one norm or the two norm. Then there will always exist a Hermitian matrix such that H is the vector. Oh, sorry. If H and lambda and R and D and lambda majorizes H, then there will exist a Hermitian matrix such that H is the vector of diagonal elements and lambda is the vector of eigenvalues. So given any two vectors that majorize each other, you can always find a matrix, a Hermitian matrix, such that one of the vectors is the eigenvalues of that matrix and the other is the diagonal elements. But you can also turn this the other way around and say that if I give you, for example, a density matrix, then it's always going to be the case that the vector of eigenvalues of this density matrix is going to majorize the vector of diagonal elements of this density matrix. Okay, and the way to prove this, and I will go through this proof because it's instructive, is if I have an H that's Hermitian, so let's call this a proof now, then I know that I can always diagonalize H. So I can always write H in the form, this is H is U inverse, WU, where this is diagonal, and U is a unitary operation. So this essentially amounts to finding the basis in which H can be expressed as a diagonal element, as a diagonal matrix, sorry. And now let me just look at the relationship between the diagonal elements of H and the elements of W. So I can write the diagonal elements of H, which I label by HII. You can write this, and this is now just matrix multiplication. This is U inverse IJ, WJ. So I can write WJK here, but I don't need to, because the only elements of W that are non-zero are the ones which have the same index between row and column. And then I have at the end U, J, I. And this is summed over J. Okay. And using the property that U is a unitary, we know that U inverse is U dagger. So this becomes sum over J, U, Ji or Ij mod squared times WJJ. But this now, UJI mod squared, I can call this a Dij. And the reason I call it Dij is because the sum over I or the sum over J of UJI mod squared is equal to 1. And this follows from the fact that in a unitary, the rows and columns are orthonormal. So the norm, the two norm, the square norm, mod squared norm of any row or any column of a unitary operator is going to be 1, which means that I essentially get now that this vector H is equal to D times lambda, where lambda is the vector of, is the diagonal elements of W, which are the eigenvalues of H, because W is essentially the diagonalization of H. And this proves the theorem that any, if I have any two vectors that majorize one another, I can find a Hermitian matrix like this. Okay, so this is very important because for two reasons. One is it says that given any density matrix, we always can find the eigenvalues, and we always can find a basis in which the matrix is diagonal, and in that basis, the set of diagonal elements, the eigenvalues, will always majorize your original one. But the reason it's also very important is because most of the thermodynamic transformations that we consider are unitary transformations. So we take rho and then we effect a transformation rho dagger, and a unitary operation does not change the eigenvalues of a density matrix. This is something that you will have learned in linear algebra. The unitary operation will only rotate the eigenvectors because it is a change of basis, But if there is an eigenvalue of the original density matrix, it's also going to be an eigenvalue of the final density matrix, which means that the vector of eigenvalues remains the same. So lambda of rho is the same as lambda of rho prime, where lambda of rho are the eigenvalues. But of course, depending on what the unitary operator is, if we fix a basis, then the vector of diagonal elements is going to look very different after every single transformation. In thermodynamics, this means that when we look at the energy eigenbasis and we do a unitary transformation, the diagonal elements are going to change a lot, but it is worth keeping in mind that no matter how they change, it's always going to be the case that the diagonal elements are majorized by the eigenvalues. And this is very important for understanding what happens at the beginning and end of any transformation. Okay, as an example, continuing in the vein that we had, so we had the vector A was 0, 2 over 3, 1 over 3, and B was 1 over 3, 1 over 3, 1 over 3. I know that, for example, I can pick my W to be this matrix, so just 0, 2 over 3, 1 over 3. But now I want to pick another density matrix that has the same eigenvalues as W, but it has, for example, but it has the diagonal elements being the values of B. And the way to do this is to simply pick just to simply change a basis into one that will give you the new diagonal elements to be those of B. Because B is a maximally mixed state, it's actually very simple to pick a basis like this. The state A corresponds to, for example, I can have the state 2 over 3, 1, 1, plus 1 over 3, 2, 2, and nothing in the state 0, for example. This will give me my state W. If I simply change to a different basis, so if I change to the basis of 0 plus omega 1 plus omega squared 2, or 0 plus omega squared 1 plus omega 2, or 0 plus 1 plus 2. This is the Fourier transform basis. Everything, of course, divided by square root of 3. And omega is equal to the cube root of 1, the complex cube root of 1. Then it's very easy to show that in this basis, if I call this phi 1, phi 2, and phi 3, you will end up getting a density matrix H where the diagonal elements are 1 over 3, 1 over 3, 1 over 3. I can leave this for you to check. In fact, you will do something similar to this in the tutorial. Okay, any questions so far? This is a very important theorem to understand. Right. Right, so as an immediate application to this, we are going to now prove the statement that we said, that we talked about earlier about the passivity of rho. So rho being a passive state, if it is diagonal and ordered in energy. And the reason for this is now very simple. The average energy of rho is, you could write it as trace of H rho, but the better way to write it is as the sum of the populations Pn, which remember are the diagonal elements in the energy eigenbasis times the energy En. And so minimizing the average energy under all unitary operations is minimizing this linear function. So this is now a linear function of the diagonal elements. And we know that the diagonal elements as a vector, so if I take P as a vector, this is always majorized by lambda, which means, and lambda again is the vector of eigenvalues, which means that P is always equal to D times lambda, no matter what unitary operation we do. Even the initial state, the values of P are always going to be given by some doubly stochastic matrix on lambda. But we already know that when we are optimizing a linear function of the diagonal elements, it's going to be a permutation of the diagonal elements. In fact, because if we are optimizing over all doubly stochastic matrices on lambda, if you're optimizing the energy, then we're going to get that the maximum and minimum value of the average energy is going to be given by a permutation of lambda. But if it's going to be given by a permutation of lambda, we're going to end up with a state whose diagonal elements are in fact the eigenvalues lambda, just permuted or changed in ordering. And the only density matrices whose diagonal elements are in fact the eigenvalues are the ones that are diagonal in that basis. Because if you're not diagonal, then your diagonal elements will not coincide with your eigenvalues. So we get that we need to be diagonal in energy, so that P is just a permutation of the eigenvalues lambda. And then the next step to say that it's ordered in energy is very trivial. To find the permutation that maximizes or minimizes the energy just by inspection, we can say that, well, we're going to put the maximum population in the ground state, the next highest population in the state that's just above that, and so on and so forth. So immediately, just using the concept of majorization and the Schur-Horn theorem, we see that by optimizing the average energy of a state, we get those states that are passive, ordered in energy, and diagonal in the energy eigenbasis. Right.
Sorry, I got a bit lost in the argument about why it's diagonal in energy.
Okay, so okay, step by step, we say that, so the final, if I look at the populations P, N, this vector, which I called P, I know that is always going to be given by a doubly stochastic matrix working on the vector of eigenvalues of the state. So any unitary operation that I make on this density matrix, the diagonal elements in the energy eigenbasis is going to be a doubly stochastic matrix times the vector of eigenvalues. Now, I want to I want to minimize the average energy, which is the minimum of Pn times En, okay, which is the same as saying it's the minimum of, I can actually call this En now, this is just a function. I can also label it by a vector, and this would be the inner product between this vector of energies and the vector of populations. So it's the minimum of this linear function on the vector P, which is the minimum of this linear function on D times lambda, which by the same thing that we argued before, this is the minimum of E times a convex combination of permutations, Pn. Now these are permutations, remember, and on lambda. And this, as we argued before, is going to be given by the minimum of this E of some permutation of lambda. Because a convex combination of permutations, the minimum of the function on this is going to be given by the minimum among just the function of the permutations of lambda. So what we get is that if we start with a state and we say that it is passive, it means that we should not be able to extract any work from it. So we should not be able to, we should not be able to do any transformation that decreases the work from it. But we already know that those states that have this average energy minimized, that you cannot have anything more done to it, the vector of populations P must be given by a permutation of the eigenvalues lambda, which means that the diagonal elements are the same as the eigenvalues. Again, when I say diagonal elements, I mean in the energy basis, because these are the Pn and these are the lambda n. So they can be ordered in whatever way you like, but the diagonal elements have to be the same as the eigenvalues. And the only matrices that have this property that the diagonal elements are the same as the eigenvalues are the ones that are essentially diagonal. Because if you have, and this is just from linear algebra, if you have an off diagonal element, then the diagonal elements are not going to be the same as the eigenvalues. Because if you take, for Hermitian matrices at least, because if you take the determinant equation to find the eigenvalues, you will find that they're different from the diagonal elements. So this last step is just from linear algebra. And so the conclusion then is that any state that starts off such that you cannot extract any energy from it, it has to already be diagonal in the energy eigenbasis, because its populations have to just be the eigenvalues of the density matrix, just reordered to be with respect to energy. Does it answer the question?
Yeah, thanks.
Perfect. Thank you. Okay, so then what is the time now? So we've gone on for an hour. Okay, so then I think this is a good time. Oh no, we haven't gone on for an hour. It's 45 minutes. But that's sort of, okay, half lecture. So at this point, we will take a break, and we can resume at 4:40. So 16:40, we'll resume the lecture. I will come back a little bit before to answer more questions if anybody has any. See you in a couple of minutes.
Okay.
Okay, so let's continue now. There's one final thing to say before we go into the notion of complete passivity, which is Schur convexity. It's another reason why majorization is extremely useful. So just to recap, the notion of a convex function in analysis is a function such that f of t x1 plus 1 minus t x2, where 0 less than t or less or equal to t less or equal to 1, is less than t f of x1 plus 1 minus t f of x2. And if you think of it as a graph, f of x versus x, these are the functions that have sort of positive curvature. That second differential, the second derivative is always greater or equal to 0, for example. Because if you mix the two functions, you get a value. So if this is a mixture of the two functions, it's larger than the corresponding mixture of the two arguments, t and 1 minus t. This is not the actual distance between x1 and x2. This is just the fractional distances. And there exists something very similar on the level of majorization, which is called Schur convexity, which is a function such that if A majorizes B, you are guaranteed that the function on A is always greater than the function on B. And similarly, there's the opposite notion of concave, a Schur concave function, which is the opposite. If A majorizes B, then the function is always less on the greater state. So examples of the following, entropy, for instance, and by entropy, I mean the Shannon entropy on the vector, is Schur concave. So if A majorizes B, then S of A is always less than S of B. This also coincides with what we saw before, that the state that majorizes every other state is the pure state, which has 0 entropy. And the state that is majorized by every other state is a maximally mixed distribution, which, as we know, is the one also maximum entropy. Yes, so now the entropy is a nice function because it's symmetric with respect to the different vector elements. It doesn't care of how you order them. If you have a function that is not symmetric, then it's never going to be Schur convex or concave. However, if you already have a pre-ordering on vectors, which is something that passivity, for example, gives you, if we limit ourselves not to any arbitrary density matrix, but just to the set of passive states, so we already have a ordering of vectors, then you have many more functions that become Schur convex or Schur concave. So for instance, if rho 1 and rho 2 are both, are passive, and rho 1 majorizes rho 2. Now remember, the reason I can write majorization on a density matrix is because we already know which basis they are diagonal in, and we are already looking at the vectors or the elements in that basis. Then I have that the ground state population, the ground state population is also follows the same thing. So this is S convex. And this is a very simple consequence of the fact that if rho 1 majorizes rho 2, then the largest element of rho 1 is just larger than the element of rho 2. And then similarly, the max excited state population is S concave, of course. And as we've already seen, the average energy is S concave. So if I have two density matrices, one of them majorizes the other, the one that majorizes the other has a smaller average energy always because of what we've just discussed. And because of this, majorization can somehow be seen as, so majorization plus passivity together, or majorization restricted to looking only at passive states, is a sort of partial thermodynamic order. And it sort of corresponds a little in some fashion to cooling. And the reason is the following. If I tell you that one state has a higher ground state population, has a smaller entropy and a smaller average energy than another state, then this somehow, these are all of the ways in which we could consider comparing the temp, like whether one state is colder than the other state or not. It has higher chance to be in the ground state, a smaller entropy, lower average energy, etc. And the reason for this is because, unlike in the case of qubits, where we discussed we can always associate a temperature, on higher dimensional states, we cannot associate a temperature. But even without just looking at only thermal states, if we just restrict ourselves to passive states, we can already form a partial ordering in terms of which states are colder in some respects than other states. There is one exception to this, and that's the free energy, which is just, we will discuss this more later, but just as a definition, it's E minus Ts, so I can write 1 over beta times S. This is not okay, and now on to the notion of complete passivity. So what we discussed so far, passivity, was when we considered that we extract work from a system, we were allowed to do a unitary on a single system or a single copy of a system. So passivity just had rho goes to u rho u dagger, but for complete passivity, what we consider is that we can take many copies of rho, so rho tensor n, and this is just a notation for this n times, and we're allowed to do a unitary on all of them. So this is now a much larger unitary on n, sorry, rho tensor n copies of rho. And this is a unitary that does not need to act locally on each copy of rho. It can effectively, it can act on many copies of rho. It can be a very highly entangling unitary, for example. And now we consider the ergotropy on this. So we say, what is the max of the trace of h, which, remember now, h acting on n copies is just going to be the sum of the local h's. So we say h1 tensor identity on the rest plus identity 1 tensor h2 tensor identity on the rest, and so on and so forth. And this acting on rho tensor n minus the same quantity acting on u rho n u dagger, and the max of all u. And I call a state rho completely passive if and only if this is 0. Okay, I just saw a question, but okay, I'll come back to this question later. Right, so the only completely passive states are those that you can not extract energy from, no matter how many copies of the state you're allowed to act on at the same time. And now we are going to prove somehow, we're going to prove that the only states that satisfy these are the Gibbs states. And we're going to prove it using the concept of virtual qubits. And this is where you see the concept of virtual qubits in action. So remember that one of the ways in which we said we were able to associate passivity is with there not being any inversions, or rather there not being any negative virtual temperatures. So if I have a state rho that is passive, then that means that all of the virtual temperatures beta ij between any states I and j that I pick in the Hamiltonian of rho must always be greater than 0. Because if I find any pair of passive states where the virtual temperature is negative, that means the higher energy has a greater population than the low energy, which means we are not ordered properly in energy, and I can just swap in and extract work. So what we're going to do now is to show that if we have a passive state that is not thermal, then we can take a sufficient number of copies of it and get such an inversion. We can get a negative temperature. And the reason is the following. If I have a state that is passive, but not thermal, then I can pick two different transitions with beta not equal to beta prime. So given the Hamiltonian of the state, and this is the Hamiltonian HS, I now am going to pick two virtual qubits. Let me pick any one of them. So for example, let me pick the first virtual qubit will be this one. And the second virtual qubit will be this one. And so I will have a delta E1 and a beta 1 and a delta E2 and a beta 2. And because the state is not a Gibbs state, I'm guaranteed that we can do this. Because if this was not possible, then it would mean that every transition we pick, we would have the same virtual temperature for all of them, meaning that every Gibbs ratio would be the same. And that essentially would mean that the state could be written as the exponential of that Gibbs ratio, that virtual temperature, single virtual temperature times the Hamiltonian. So by construction, if it's passive but it's not thermal, we can always pick two states that have this property. Right, and now I'm going to let me call this state I, J, and these states K and L. So now what we're going to do is we are going to compose many copies of the state. So what we're going to take now is rho tensored M plus N. So I'm going to take, which is the same as saying rho tensored M, tensor rho tensor N. So this is a very high joint state of it's a highly composite state of the system. And I'm going to look at two energy levels in this state. And these are the energy levels I tensored M, tensored L, tensored N, and the state J, tensored M, tensored K, tensor N. What this corresponds to, using the diagrams that we're used to, is I have M times these states. So this is the I on the first system, J on the first system, I on the second system, J on the second system, and so on, tensored with N times. And this is K on the, this is going to be the M plus 1 system, L on the M plus 1 system, and so on and so forth. And this is going to, of course, give me a composite system that has many, many virtual qubits, but I only care about a single transition. And the transition that we care about is the following. It's the one where all of these go down in energy and all of those go up in energy. So it's a switch where all of the M copies go from the excited to the non-excited state, and all of the N copies do the opposite, which is essentially the two states here that I've written. And now I want to write down, so what is the virtual temperature of this transition? And from last week's lecture and today's tutorial, this should go pretty quickly. The energy difference of this transition is given by M times the energy difference 1, which is the energy difference between J. So the energy difference between J and I is given by delta E1. And then it's going to be minus N times the energy difference of 2. Because whenever we do this transition from I to J, IL to JK, we go up delta E1, but we go down delta E2. So the energy difference is going to be given by this. And if I take the ratio of populations, so P of I tensor M, or rather, I've ordered it in this manner. So J tensor M tensor K tensor N divided by P of I tensor M tensor L tensor N, then this, because it's a product state of all of them, as we've done before, we can simply write each population as the product of all of the individual populations. And so this splits up into the Gibbs ratio Pj upon Pi to the power M, Pk, Pl to the power N. And this we already know is e to the minus beta 1 delta E1, e to the minus beta 2 delta E2. But this, by the definition of the virtual temperature, is e to the minus beta virtual times the delta E of the final thing. So I'm just going to call that delta E, which gives us the equation beta V is going to be beta 1 delta E1 minus beta 2 delta E2. Oh, sorry, I forgot an M here, and I forgot an N here. So M times beta 1 delta E1 minus N times that upon the total delta E, which I've written up there, is just M delta E1 minus N delta E2. And another way of writing this would be beta 1 delta E1 minus N over M beta 2 delta E2 upon the same thing, N over M delta E2. Now, this number, N over M, can be chosen to be as close to any number X on the real line as we like. I mean, it's an arbitrary rational number. We are free to choose the integers N and M as we like. So we can always pick it to be arbitrarily close to anything. And in fact, you can easily show that you can pick it so that this whole expression turns out to be negative. So for example, if you pick delta delta E2 upon delta E1 less than, M over N less than delta E2 times beta 2 upon delta E1 times beta 1, then it will be the case that this value is negative. Which means that given, so let's recap what we've just said. We started with a state that was passive but not thermal. We said we can definitely pick two transitions from this that have different virtual temperatures. And given these two transitions with different virtual temperatures, what we can always do is construct a sufficient number of copies of the state such that the joint state has an inversion, which means the joint state is not passive and we can extract work from it. So any state that is passive but not thermal, we can extract work from. There are some intricacies in this proof as to if you have to pick two energy levels that are not the same gap, and of course, and how to prove that there will always be such transitions in a state that is passive but not thermal. We will not discuss them here. You can convince yourself that even if you have degeneracies, you can always still do this when you have a non-thermal state, that you can pick transitions with different energies that have different virtual temperatures. And so therefore, it means that the only completely passive states are the Gibbs states, e to the minus beta times h upon the partition function. Are there any questions as to this proof? None? All right. Okay, so this is quite neat because what we've done is that we've shown that the thermal state is kind of special in thermodynamics. You cannot extract any work no matter how many copies you have. And this is in fact now the first example of a resource theory. So what is a resource theory in general? A resource theory, especially one in thermodynamics, consists of, you have sort of a paradigm where you have states and allowed operations. So you have a set of states that you can do something with, and you have a set of operations that you're allowed to perform on the states for free. So they're essentially the set of operations that you do not have to pay anything to do. And you have some resource that you're keeping track of. So in our case, our states were general arbitrary density matrices rho, our allowed operations were unitaries, and our resource was the ergotropy, so which is the same as the work extractable from a quantum state. And the result of this resource theory is to get some sort of, you get the set of free states, and sometimes you get a resource monotone. So effectively, the ingredients of a resource theory is the set of states and allowed operations. And what you get out of that is you get the set of free states, which are the things that you cannot extract any resource from. And sometimes you also get a resource monotone, which is a constraint on what state you are allowed to transform into what other state, or the amount of resource that you can get. So different resource theories, and we will discuss a number of them in the future, will have different results for these free states and monotones. But in our case, we can see what we got is that in the case, if U single copy was allowed, then the free states were the passive states. But if U multi-copy were allowed, then we got that the free states were the Gibbs states. And this is a general feature of resource theories. It's very sensitive to what you allow as the operations. In the first case, the allowed operations are more restrictive than the second case, because single copy unitaries, of course, are more restrictive than unitaries on multiple systems. And as a result, the set of free states is larger in the first case. You have any passive state, whereas in the second case, you have only the Gibbs state. And in the second case, we get a sort of constraint, which in fact is a version of the second law of thermodynamics, which is no work extracted from any number of copies of this thermal state rho. And this is going to link very much into the concept of a thermal bath, because as we know from classical thermodynamics, one of the statements of the second law is that you cannot extract work from heat, which is the same as saying if you change the energy of a thermal bath, you are necessarily not going to be able to extract work. You can only increase the energy of a thermal bath by doing a unitary on it. And so this is really the first example of a resource theory that we will come across.
I have a question. How
Yes?
do we achieve the different copies of the state? Don't we have the no cloning theorem that doesn't allow us to make direct copies of the state, or how do we generate this NNM copies?
So this is not so much of a, so the generation is not part of the protocol. So you're simply given many copies of the state. So you can imagine it in the following: when I'm given a thermal bath, it's essentially the same as saying I'm given many copies of something, or I'm given many particles together. So the resource theory here is defined as you're given as many copies as you like of this state rho. So somebody has prepared an ensemble of states in this known density matrix, and then you're allowed to do any operation you like on it. So in fact, in some sense, this density matrix is not an unknown, it's a known density matrix. So you know what the density matrix is, which is different from the case of cloning, because the whole point of the no cloning theorem is that you cannot clone an arbitrary unknown quantum state. If you know a quantum state, then of course you can clone it. You just have to prepare the same state. But if you have an unknown quantum state, you cannot clone it. Here we don't, the state is known. The density matrix rho is known. You have many copies of it, and you're allowed to pick a unitary to extract work from it.
Okay, and another question for the proof of the Gibbs state, the previous proof. We use several uses of the swap unitary, right? And that swap unitary we had said before that has a certain delta of energy on the state after it's applied.
Yes.
So
well, actually, so in fact, it's not many copies of the swap. It's a single swap, because the swap that I'm doing is the unitary that swaps these two states. So the unitary is going to be identity on the rest of all of the states in the joint state, plus these I tensor M, L tensor N with J tensor M, K tensor N, plus the Hermitian conjugate, which is these swapped together. So this is still this is a single unitary operation that just swaps these two energy levels. And the energy cost of this is going to be given, as with the original swap, it's just going to be given by delta P times delta E. This is something that always happens at the end of a single qubit swap between two energy levels. The work cost or the work difference that is there at the end is given by the population that is being moved across it times the energy difference. Now, I haven't calculated this explicitly, and the reason for this is because we qubit that as long as the virtual temperature is negative, then we can extract energy. And that was the purpose of the original statement of the, where is it? Of passivity. So as long as I have two levels that have the property that the higher energy level has a higher population, then, which is the same as saying that beta virtual is less than 0, then it is definitely non-passive, because I can just do the X operation, and this will result in the like in this case, for example, I will extract W equal to 0.2, which is the change in population. If I switch this times E, which is the energy gap of that. So we already know that in any system that we have, a negative virtual temperature is going to give us a positive work that we can extract. So all I have to prove then, in the case of completely passivity, is that when we have a state that is passive but not thermal, we can construct one pair of energy levels in a composite joint state that has a negative virtual temperature. Yes.
Okay, thanks a lot.
Any other questions? You're welcome. Okay. Right. So this is very nice because we have a sufficient amount of time. And in this time, I am now going to present the next very big topic for us, which is, well, so I'm going to just keep on discussing the thermal state, but I'm going to do it from the perspective now of entropy and Jaynes' principle. Okay, so the thermal state is a very, but the thermal state, I keep saying thermal state, and I do mean Gibbs state, even though I feel like I haven't yet justified why we call it the thermal state. At the end of this lecture, I will not have to say Gibbs state any longer. Yes, is this the case, that the audio is very delayed for other people? Oh, I actually see it between my different devices as well. Is it sufficient to cause a problem?
No, it's not much of a deal.
Yeah, I can see it as like a fraction of a second later. The video is a fraction of a second different from the audio.
I think it also happened in previous lectures, but at some point it just levels out. I don't know what happens.
I see. Okay. So maybe then at some point the internet will just catch up. I hope that will happen. All right, but ask a question if that has caused a problem in understanding. Okay, so we have now seen one way of arriving at the Gibbs state, which is we defined a resource theory, what we're allowed to do. We're allowed to do unitary operations on multiple copies of a state. And we found that the Gibbs state was the only one that would not allow us to extract any work, no matter how many copies we have. Now we're going to find a different way of looking at the same thing, which is Jaynes' principle. Okay, and what is Jaynes' principle? This is a bit of a philosophical principle. It's by a very clever statistician or mathematician called E.T. Jaynes, who argued that when we have a situation in which we do not have complete information about the state of a system. So we have a system, but we don't know as much as is possible to know about it. We only know a subset of information. And we are asked to then guess something about the system, either guess what the outcomes of a measurement on that system are, essentially to guess what the state of the system is, consistent with the knowledge that we have. Jaynes argued that the best description of the state is the one that has the maximum entropy given the information that we already have, which is effectively to say that we should not know anything more than the knowledge we already have. And because entropy encodes the knowledge about a system, if we search for all of the states that have the same amount of that knowledge, we should pick the one that are maximal entropic with respect to all of the other degrees of freedom that we possess. So this is the notion of Jaynes' principle. So as a very simple application, if we have, if we have a system S and we know nothing about it, then Jaynes' principle would say that the best guess of the density matrix of the system is just the maximally mixed state, identity over D. And this is S associated with a Hilbert space of dimension D. So this is a very trivial application of it. If we know nothing, then it must be the maximally mixed density matrix, because that's the one of maximal entropy. But in many other cases, we can have partial information. And in particular, in the case of thermodynamics, one of the things that we know very often about the system is the energy of a system. So for example, I can have a glass of water, and I can put into it a cube of ice, or I can heat it by a certain amount. I can add a certain amount of energy to it via a chemical reaction or some other reaction, and I will know how much energy I've put into it. So I can keep track of the energy that's put in the water, even though I cannot keep track of all of the microscopic degrees of freedom of the water. I cannot keep track of the velocities and the positions of every one of the particles in the glass of water. So one of the interesting cases in thermodynamics is, what if we know the average energy E, which is trace of the Hamiltonian times rho? Then what is rho by Jaynes' principle? And so now this, as a formal question, is find the maximum over all rho of the entropy of rho, such that trace of H rho is equal to something that's given to us. That's some E average. Okay. Okay, and as you might expect, what we get is a Gibbs state. And the way of arguing it is, there are multiple ways of arguing this, and I like to argue it in two steps. The first step is to argue that the density matrix that maximizes the entropy given a fixed average energy is always going to be diagonal in the energy eigenbasis. And the reason is the following. If you have, imagine that, take rho non-diagonal in energy, so let it have some coherences in energy, then you're going to have some subspace of rho. So you're going to have, well, actually, yes. So you're going to have some subspace of rho where you're going to have some diagonal element PMM, so rho MM rather, rho NN, and some off diagonal elements here. Let's call this C and C star. Okay. So this is going to be the form of rho with all other arbitrary elements. And what I can do is I can simply take now this same density matrix and set those elements to 0. This is a valid operation. This is actually a type of dephasing operation where I simply imagine that I've made a projective measurement of the energy eigenbasis, and I don't record the outcome of that. The end result of the measurement is going to be a density matrix where all of the off-diagonal elements in energy have vanished. Now, these two density matrices, if I call this rho, sorry, rho and rho prime, the trace, the average energy of rho is equal to the average energy of rho prime. And the reason is because the average energy just depends on the diagonal elements in the energy eigenbasis, and those haven't changed. But the what we see is that the diagonal elements of H, so sorry, the diagonal elements of rho. So if I write the diagonal elements of rho, this is equal to the diagonal elements of rho prime. However, the diagonal elements of rho prime, this, I needed more space. Let me write it out completely. The eigenvalues of rho strictly majorize the diagonal elements of rho, because rho is not a diagonal matrix. But the diagonal elements of rho prime are exactly the same as the eigenvalues of rho prime. So I use lambda to say the vector of eigenvalues, because rho prime is a diagonal density matrix. So what I've taken from rho to rho prime is I've just set all of the off-diagonal elements to 0. And this means, so if we see this, now this is, if we connect all of these, it means that lambda of rho majorizes lambda of rho prime, which means that the entropy of rho is going to be less than the entropy of rho prime. And this is where Schur convexity comes into play. So what I've done is I've taken a state, which is off-diagonal energy, I've kept the average energy the same, and I've increased the entropy. So clearly it cannot be that the states that maximize the entropy for a fixed average energy are off-diagonal, because I've just shown that if you start with one like that, you can actually get even higher energy, sorry, even higher entropy. Okay, so this already shows that rho has to be diagonal, and then rho is going to be of the form sum over Pn of En, and the entropy then is minus, let's say, K Pn log Pn. Sorry, I should say, I forgot to say at the beginning of the lecture, what I'm going to do is link the Shannon or the von Neumann entropy, which comes from information theory, to the concept of thermodynamic entropy, which is the differential of heat. But right now I'm working with the Shannon entropy. So by entropy here, I mean the von Neumann entropy of the density matrix, which is defined as the Shannon entropy of the eigenvalues. So this is also the same as minus K trace of rho log rho when I write it in terms of the matrix logarithm. Okay. And so the next step is actually something that I will not go into detail, and this is a good exercise for you to do, is to just optimize S with respect to average energy. So I can do this by just forming a Lagrangian, which is given by S of rho. And then of course I have a multiplier for the normalization. So the sum of over n of Pn must be equal to 1. And then I have another normalization for the average energy. Pn En must be equal to the average energy. So from your, I hope you have crossed Lagrangian optimization at some point or the other. If you do this and then you differentiate this Lagrangian with respect to Pn and you set it to 0, what you will end up getting is that Pn goes as the exponential of e to the minus some factor, which we might as well now call beta En, which then gives us that rho is e to the minus beta Hn by Z. Okay, so what we've proven is that if I look at any state that has a particular fixed average energy and I find the state of maximum entropy, this is going to give me a thermal state. So thermal states have the property, the two properties, they maximize S given E average. And also you can check, because it's sort of a monotonic and a strict monotonic relationship, you can also check that they minimize E average given S. So if I fix the entropy of a state and I ask what is the minimum amount of average energy given this entropy, it's also going to end up being a thermal state. And this is actually kind of useful because given an arbitrary density matrix rho, which is not thermal, I can always associate two temperatures with this state. I can always go to tau max which is this one, or I can go to tau minimum, which is this one, and T minimum is going to be less than T maximum, or conversely, beta minimum is going to be greater than beta maximum, which is the same as saying that on the graph of, if I fill in the graph of the entropy and the energy, the thermal states are going to form a particular line on this graph, but given any arbitrary density matrix rho, I can either go to the thermal state of the same entropy. Oh, I'm sorry. I believe I have drawn this the opposite way. So if I have the thermal states are the one that for fixed energy maxima. So there's nothing in this region. And if I'm here, I can either go maximize the entropy or minimize the energy. This is rho, this is tau max, this is tau minimum. So this is another way of not associating a single temperature with a state, but associating a range of temperatures to a state. Somehow you can understand that for a lot of purposes, this arbitrary density matrix can be understood to behave somewhat in between these two temperatures. Are there any questions at this moment? Let me look at the chat. Okay. All right. So the final thing I will discuss in this lecture now is the link between the von Neumann entropy and thermodynamic entropy. Okay. So the way I'm going to do this is by doing the following sort of thought experiment. Imagine that I start with a thermal state tau, and I give it energy. So I give it an energy delta E, and I keep it thermal. So this really now is what we're doing here is we are discussing one of the major properties of a thermal bath. When I say that I have a thermal state tau, I give it energy, and I consider that it stays thermal. We already know that thermal states by Jaynes' principle maximize the entropy. This is the same thing as saying, I'm going to take a state that was already maximal entropic for its energy. I'm going to give it some energy, and I'm going to ensure that it stays maximal entropic for that new value of energy, which is the same as saying that this energy has been exchanged at the minimum information. So I know no information about the state other than its energy. And this is very important because I could imagine, for instance, starting with the thermal state and doing a very specific operation on it, doing a very specific swap in the energy eigenstates, for example. And in that case, the entropy would not be maximized because I would have known how the system changed. So what I'm doing with this assumption is I'm saying, I only know the energy that has been done, but I don't know how it was done. In fact, my knowledge of how it was done is minimal in the sense that the entropy is maximized. So what I'm going to do is I'm going to take tau and I'm going to do this. Actually, I'm going to make it dE, a differential amount of energy, so a very small amount so that I can do a differential. And I'm going to ask how does S and beta change with respect to this. So it turns out actually that the easier way to do this is not actually to consider the differential with respect to energy, but rather the differential with respect to beta. So I'm going to have rho equal to e to the minus beta h upon z, and it's going to go to e to the minus beta plus d beta h upon z prime. And what we're going to do is we're going to calculate what the rate of change of entropy with respect to beta is, and what the rate of change of average energy with respect to beta is. And this is quite simple to do. Let's consider the rate of change of entropy. This is the differential with respect to beta, sum over n pn log pn. And sorry, I should never forget the minus sign. I'm also going to take that this k, by the way, is it's called the Gibbs factor. I think it's called the Gibbs factor to define the entropy. So the entropy is the Shannon entropy multiplied by k every single time. And now this, we can simply take all of this inside. And the differential of this is 1 plus log Pn times dPn by d beta. But Pn, of course, is e to the minus beta En upon Z. So this gives us minus K and the sum over N. Oh, actually, in fact, I do not want to do that. I don't want to simplify dPn by d beta. I want to simplify log of Pn. This is minus beta En minus log of Z. Because if I take the logarithm of this, that's what I want. That's what I'm going to get. dPn by d beta. And now this is just going to be given by plus beta sum over N En dPn by d beta. And the reason is that these two terms, 1 and log Z, they can come out of the sum. And the sum over N of dPn by d beta is the same as the derivative with respect to beta of the sum over nPn. But this is a normalized state. So this derivative is 0 because the trace of the matrix, the sum of the diagonal elements, is always 0. So this is what we get. But this, in turn, is very simply plus beta d over d, because E is a constant, which is plus beta times d of the average energy by d beta. And so all I have to do now to complete the connection between information-theoretic and von Neumann entropy is to say, well, if I have a state that's thermal and it remains thermal, then what I'm going to find, then what I'm going to do is I'm going to associate that energy exchange with the thermal state as heat. So I'm going to write dE, or d of average energy, as dq. And then what I have, very simply, what I've proven here is that ds is equal to, I believe I forgot a k everywhere, plus k plus k. This is equal to k beta dq, dq, which is the same as dq over t. And this is my thermodynamic entropy. And so we see from the definition of heat being energy exchanged via Jaynes' principle, so energy exchanged at the maximum uncertainty or the least information with a state that always stays maximally entropic, then we get that the change in the Shannon or von Neumann entropy is the same as the differential of the heat. So there's a very, well, this says that the information-theoretic and thermodynamic meanings of entropy are essentially equivalent. Is there a question here? Okay, so to complete this, I will do one more thing, which is to say, well, what we've argued here is that for a differential change in the energy, we have this relationship. But of course, notice that beta also changes. We differentiated with respect to the temperature. And so the temperature also changes. For a thermal state or a thermal bath, what we would like is that the temperature doesn't change. And the way to argue this is quite simple. We simply take tau tensor n. And as an exercise that you will do in a tutorial, what you will show is that if you consider d beta by dE, or it's the same by our notion of d beta by dQ, this scales as 1 over n squared, meaning that if I give a particular unit of energy to a single copy of a system, the temperature change of that compared to the temperature change if I gave the same amount of energy to n copies of the system, the temperature change with n copies would be 1 over n squared. Therefore, if n is large enough, I have that beta remains the same. And so this is now really the basic definition of a thermal bath. It is always at the maximum entropy, given the knowledge of the energy. And even in the case of more complicated thermal baths, you only have a few parameters, big parameters of the bath, but it is a maximal entropic state. So it is in a, well, I would say Gibbs state, because saying thermal state is a bit redundant here. And the fact that it is large enough that the temperature does not change. So the two defining properties of a thermal bath in thermodynamics are, one, that information is always lost to thermal baths. You always exchange big parameters without any knowledge of the microscopic details. And the second is that it is large enough so as to not be affected by the change in parameters, in the sense that the temperature that defines the bath always remains the same. Okay, with that, I think we have concluded everything we would have liked to discuss in this lecture. Are there any final questions? Okay. Okay, in that case, I think that will conclude this lecture. And in the next lecture, we will continue with the information theoretic manner of looking at thermodynamics. So we will discuss things like erasure and Maxwell's demon, and finish those building blocks in order to continue then in the lecture after that, covering as much of quantum thermodynamic research as we possibly can. Thank you, everybody, and have a good evening.
Thank you. Have a good evening too.
Thank you.